Good rainy afternoon. So I'm delighted to introduce Brandon Kruysman and Jonathan Proto, the first SCI-Arc Robot House Research Fellows. And the fellowship was launched last September thanks to Eric, Ming, Jamie, and SCI-Arc board members' initiative. This month marks the first anniversary of the opening of the Robot House, and it's been an incredibly exciting and productive year. So in addition to having the distinction of being the first two research and teaching fellows, Brandon and Jonathan are also the first two graduates of the new EST program launched by Ming last year. With their teammate, Karime Batliner, they were awarded a 2011 SCI-Arc Thesis Prize. Their thesis prep research on synchronous robotics was also selected for publication in the Rice Architectural Journal last year. Building on their thesis, advised by Devin Weiser and myself, the fellows have gone on to develop a Maya-based and designer-friendly interface that's now being used in studios, seminars, and new thesis projects at SCI-Arc. Their support of studios and seminars as a platform to develop and test new tools and techniques, particular to SCI-Arc, has been really rewarding for all of us involved. They've effectively built a SCI-Arc-specific interface for robotics. Brandon and Jonathan are a consummate team with complementary skills. Brandon, a gifted programmer, Jonathan, a digital craftsman. They came to SCI-Arc's graduate program as accomplished makers with degrees in architecture from Philadelphia University and an impressive portfolio of advanced design research and several built works. Their background at the cutting edge of digital fabrication included collaboration in New York with Mark Furness on several important and challenging installations by the ever many. As both SCI-Arc graduates and fellows, this team honors and contributes to the vitality of SCI-Arc as the school continues to push boundaries and break down digital and physical worlds. Across media, blazing trails into the post-medium condition. Please join me in enthusiastically welcoming the fellows.
Thank you, Peter, for the introduction. We'd like to thank everybody for coming. We're really excited to share some of the work that's been going on in the Robot House for the past 8 months. First, we'd like to thank Eric, Ming, and Jamie, and many others for putting together this fellowship. It's been a really rewarding experience for both of us. We'd also like to thank the generous contributions from the Fletcher Jones Foundation and the Parsons Foundation. And we'd also like to thank Peter, Devin, and Andrew, who have been instrumental in the development of the robotics lab and tremendously supportive throughout this fellowship. Brandon and I have had a rather unique experience with the way we've come into working with robotics. And this really has to do with the 6 months that we spent working with Peter during our graduate studies prior to the robots even arriving at SCI-Arc. This was conceptually an extremely important time for us, but even more so technically. We developed a digital tool set that has become the foundation of our research within the robotics lab. Ironically, this was all accomplished through exercises of simulation and essentially faking what we could do with the robots when they finally would arrive. So for us, the robots here at SCI-Arc have always existed in two radically different worlds. In one, they are bound by physics and reduced to their material properties. In the other, they are defined algorithmically and only limited by our processing power. This duality has changed the way in which we approach the newest addition to our tool set. While we have previously relied on units of measurement, inches or millimeters, to define precision, we are experiencing a shift in this unit. Our precision is defined through the keyframe, or 1/24th of a second. This unit is the link between our digital platform and its physical counterpart. As designers, the exchange between these two worlds is how we define our own creative space. We understand this exchange as a series of translations, creating a form of communication between the two. We will be showing you how over the past 8 months these worlds have come into conversation, opening new ways for us as designers to interface with complex technology. First, we're going to describe the platform at its current state, how it works, and some of the major hurdles that we have come up against. Then we're going to show you how this information has been disseminated into focus studios and seminars engaging this particular technology. Finally, we'll show a series of experiments that we feel set up some of the major research trajectories for the SCI-Arc robot house as a result of the specific context it is in. The platform that we have been developing, which is still very much a work in progress, is affectionately referred to as Esperanto. It is comprised of 3 discrete components. The first is a software plugin which runs out of Maya and translates character animation into executable motion paths for the physical robots. This has been Brandon's main focus of development during the fellowship. The second is its hardware counterpart, which has been the focus of my research. This includes the integration of external mechanisms such as end-arm tooling into our digital workflow. And last but certainly not least is what we refer to as Charla, which is the communication component essential to the multi-robot configuration of the lab.
Okay, so what we found out really quickly, almost immediately, was that industrial robotics as an industry is very closed and mostly based around conversations of efficiency and issues regarding labor. Therefore, as designers, there's little to no software that allows us to work in the creative space that we wanted to be in. Given the lab and the complexity of the multi-robot configuration, we needed a platform that could allow us to think creatively about motion, choreography, and issues regarding timing. We could have gone through many different softwares, but we chose Maya because of its power as a simulation tool as well as being a time-based platform. So the core idea of Esperanto is to use animation techniques to drive machines. Esperanto is a translator of information and allows for this communication to occur. So we're doing this through character rigging, the same concept used in the film industry. We are just rigging robots instead. And this idea opens up some new potentials of control over robots. We have experimented with a range of rigs, from standard methods of control, such as forward kinematics and inverse kinematics, to hybrid rigs that use one skeleton to control multiple robots. So by rigging, we can understand the core concepts in motion control and have the ability to understand movement in a unique way. It has also influenced how we think about tooling as an extension of the character skeleton. So we have developed a couple main ways to work with the robots. The one is the standard pre-programmed method, which inherently takes your animation and turns it into motion. We have now also integrated other types of information into the animation, where we can animate tooling, for example, airbrushes or grippers, and that can be translated into the robot's inputs and outputs. Also, robot communication for synchronous motion, which we'll get into more later. But the second way of controlling the robots, which is still in beta mode, is real-time control using TCP Python programming. And this is exciting to us because we can start to have feedback and have the robots react to information in the real environment. Okay, so the lab didn't come with any end arm tools. They're just robot arms with nothing on the end. So we were square one with tools, and this allowed for us to rethink what they should be and how we should design them. We thought of the tools as smaller machines within the larger network of the robotic cell. They have their own behaviors that are separate from the robots. They could be defined by a simple on or off switch, or have the ability to have feedback, such as a Kinect or any other sensor technology. So the design of the tool is very much part of the process. We've been working to build a variety of tools, both using pneumatics and digital outputs. Some are directly linked to material processes, and others are image-based, such as cameras or projectors, which change the way we think about ideas regarding representation. These tools have also pushed the software side, now integrated into the Maya interface, having the ability to control and study them more intensely in a digital environment. Okay, so typically tooling in robotics has a certain permanence to it. It's very expensive and engineered to perform a certain function which has been proven and tested. Our approach doesn't necessarily fit within this framework. We need tools for prototyping where the tooling develops in parallel with design ideas. Scudo attempts to address this by giving a platform that is flexible and adaptable for designers. So we've interpreted the idea of a shield, which in electronics terms helps to transfer signals across multiple components. This allows us to take advantage of commonly used lower-level electronics such as the Arduino and its open-source community for the prototyping of robotic tooling. It also allows students or designers to prototype at their desk, where you can literally animate your tooling through the Maya platform before you come into the lab. So this is an example of the first prototype of Scudo with all of its components. It was used in an exercise where we designed our own gripper, which was driven by a simple servo motor in our Arduino program. Okay, so now that we have motion and tooling, we still haven't really addressed the real complexities of the lab, which is coordinating multiple machines at once. And let's just say that it's hard to not allow these robots to collide. They're always in each other's space. So even though they're all sitting in a room together and appear as if they're operating as one machine, the realization is that they're not. Essentially, each robot has its own computer or brain and has no awareness of the others around them. So we developed an additional software component that was made as a way for the robots or additional tooling to communicate with each other in the larger network. This has influenced our work both in terms of control, but more importantly, conceptually, where all of these components are considered nodes in a network, which is constantly updating and shifting over time. It is comparable to ideas in choreography with people such as William Forsythe and Merce Cunningham, which has been extremely influential in our work. So the Charla system is scripted in Python using techniques of synchronous programming, which allows for the robots to send information to a server, which oversees the global clock of the robotic cell. This allows for a higher level of understanding of when and where the robots are at specified moments in time, which gives us confidence that we will avoid things such as collision. So in this video, the robots are moving extremely fast and in each other's work sphere, which can only be done with this software. Okay, so there were two versions of this system. The first, which was done using hardware and mechanical relays, and the latest version, which uses TCP communication, which is far faster and more reliable.
So one of the things that we've experienced while working in the lab is that you immediately find out it's impossible to work by yourself, and sharing information is integral to doing any quality work in the robot house. We initially thought that the focus was how the robots collaborate with each other, but quickly realized it's about how we as designers collaborate and share information. By the end of the fall semester, we developed the first pass at a SCI-Arc specific robotics primer, which gives people an overview of the software and how animation techniques are translated into robotic motion control. In parallel to the primer, we developed an internet presence that was a way for us to quickly distribute template files, utility scripts, which allowed for students to quickly get on the platform and operate within the complex environment. There is also a series of video tutorials that cover major topics ranging from motion control to end-arm tooling, simulation, and synchronous robotics. In the spring of In the spring of 2012, within Peter Testa's studio, we developed a series of smaller workshops called Python Bites, where we worked with students teaching advanced scripting techniques that are specific to the context of the lab. Maya animation techniques in parallel with physical computing exercises gave the students a foundation of all the necessary tools it would take to work within the lab. Over the summer, we'll be holding another workshop within the first week or two that's focusing on synchronous tasks, so moving beyond the singular robot, and later on we're going to be showing an exercise that was the precursor to the workshop. So with the establishment of this platform, we feel that a really strong foundation had been laid to continue to build upon. As a result of working through this process from its inception, we have confidently identified major research trajectories that are specific to the configuration of this lab. This understanding has only been made possible by our interactions with students and faculty members engaging similar questions. Our agendas have evolved in parallel, and we would like to believe that this is the main reason why the work in the Robot House has matured so quickly. In the next section, we are going to look at 3 different topics of research and show how initial studies started by us have been taken on and expanded by students in their own work. One of the first exercises we finished in the fall was to get the robots to pass around a block of foam. This was in part done for a demonstration for a local event called Dorkbot, which was held at the Robot House one weekend. So that seems simple, right? This work has been done in Peter's studio by a group of students during the fall who used the logic of the Charla system but incorporated a dynamic material to study the effects of coordinated motion. When we first started in September, we were only able to work with passive tools, meaning that they were either always on or always off. Over the fall, we figured out how to control the pneumatics and digital outputs which are embedded in the machines. This is the basis for any complex tooling. This clip shows an experiment that it's an ongoing exercise that's using a repurposed heat gun and a pneumatic gripper. This is work done by the Glusions, which was started in Andrew's seminar over the fall and has continued in Peter's studio over the spring. It involves a repurposed glue gun in conjunction with a pneumatic piston. Their work focuses on highly repetitive sequences where they can study material interaction over time. The final topic addresses material feedback and sensor information, or any other type of data that can be fed back into the robots. This topic is really important in any advanced fabrication scenario, and we are only starting to see the potentials of this way of working. Frankly, there are many misconceptions on what it means to sense with these robots. Because we are not interested in artificial intelligence for its own sake, we are working to find more creative ways of extracting information from our physical space as a new source for our digital space. This is a clip that shows a robot with a camera and a scanner, an experiment that we did in collaboration with Kruysman and Jonathan. It stitches together point cloud information and matches it with a dynamic camera. We then populated this digital point cloud through a process of voxelization as a way of interpreting this information. One of our interests in this project has to do with the constant recalibration of resolution, which I think this is an ongoing theme that has being discussed within the robotics lab. This is a project in process by Kyle and Liz van Hasselen. They are in the middle of an intense investigation of how to use this information in new ways, how you represent it, and literally how to use it as a tool to create objects. This is a slide of what they refer to as tomographic projections. We've also benefited from a collaboration with Devin Weiser and her students in the Rococo seminar. that uses robots as drawing machines and focuses on airbrush techniques as a way to explore highly articulated conditions of point, line, and surface, which the opening is right behind us, which you guys should check out. This was a great experience for us, and it forced us to rethink our own workflow, and how to help students come right into the lab and immediately start working. This is a clip from one of the group's portrait series.
Okay, so now we're going to discuss some of the experiments that we've been doing. So to us as designers, the most interesting space to work is between the virtual world and physical world, moving between the two in order to understand them better, giving us a creative space to work. Much of the work has been about the communication and coordination between these two realms. We've been conducting experiments that exist between images, objects, and materials. Sometimes the experiment is about material that makes an image, or about materials that make an object. Some of the more abstract projects deal primarily with issues of representation, and some more about material investigations, but all of them deal with an intense attention to scale within the context of the lab, which is the key frame. We believe that these parallel tracks of projects feed into each other and push the platform to a way of working that is not solely about fabrication, but new ways of perceiving and making space. So this project was the initial proof of concept of our interest in the camera as a way to move between both worlds, both virtually and physically. The camera gives us a point of view through the perspective of the robot. This project was done in our graduate thesis in full collaboration with Kruysman and Jonathan. So we're going to show you a clip of how we're able to move from digital space to physical and back to digital through compositing techniques. This is done by having both the camera represented physically in the lab and digitally through Maya, and matched by a highly precise motion path. So these techniques are typically found in film, but given our lab, these experiments have everything to do with motion and objects in space and time. They give us a way to literally overlay the two worlds and have provided much feedback in our ability to control multiple machines or mediums at once. This is what we're calling generative representation. Okay, so the next exercise is a progression of the last, where the camera is not only giving us information regarding timing and motion, but also acts as a scanner, reconstructing the objects geometrically in space from a series of frames in a movie. This image represents the space and time with the robot's motion path. And this is an animation of the camera and what it's seeing along the robotic motion path. So the physical space in the lab is represented virtually. Okay, so the subject of this exercise was a bowl of fruit. We used this as a way for the camera to easily recognize multiple objects so that it could cleanly construct a 3D model from overlapping photos. So the picture on the right is an image of the overlay of the digital model, textured digital model, and the real fruit. The picture to the left is a texture map for the 3D model. So this movie shows the overlay of both virtual and physical spaces along a complex motion path performed by the robot. The physical timing of the robot along a motion path is coordinated with the virtual animation. And this next image shows the transformation of the objects in time. Okay, so I'm sure some of you may have heard, but we sprayed supermodels in the lab. This was unique for us in a lot of ways, but it was the first that put as much importance on motion and choreography than anything else. Our work has always tried to do this, focusing more on motion and the formal potentials of the movement. This gave us the opportunity to do so. This is an image of the tracings of the motion of the two robots. And this is a test and our first attempt at fashion. Okay, so the setup is a two-robot collaboration, moving and spraying a model on a rotating pedestal. We've put together a simulation of the event. And this is a sequence of the model on the pedestal moving with the robots. Okay, so this next exercise is the basis of a workshop that we'll be holding over the summer. It deals primarily with two main ideas. One has to do with the analysis and representation of objects in motion, and the other deals with coordinated motion and the assembling, reconfiguring, and disassembling of an object. And this is a sample movie which shows the primitive that is exploded and put back together in two different configurations, where the robot straight ahead finds himself inside the box. Okay, so the next is the final movie of the exercise. Okay, so this is the last experiment that we're going to share. This project shows the complexities and opportunities of the robot house. It's a collaboration of all 5 robots with different tools and tasks operating as one large network. Ideas of representation are embedded into the sequence, as well as material behavior and synchronous motion and tooling. We believe that this is the first step to a much larger idea of advanced fabrication and design. So the exercise used heat as a way to transform plastic components in the form of piles and stacks, and also used paint as an additional process within the robotic sequence to get various levels of transparency. So in this setup, Robot 4 is the heater, Robot 5 is the gripper, Robot 3 is the painter, and Robot 2 is holding a work surface, and Robot 1 is filming the entire process, moving with the plastic components. And this is the sequence. The programming of the robots are done in a way that the robot tasks are offset, meaning when one robot moves to get another piece of material, two of the other robots work together to paint the pieces that are already placed. And also we design the sequence so that the work surface is dynamic, where it can move into neighboring robots' work spheres for collaboration while having an extremely accurate way of positioning where the plastic pieces are in space. So we did many tests of calibration with the heater that associated timing with formal implications. This allowed us to operate within a space that was between control and wildness. We could move back and forth between piles and stacks depending upon the amount of heat applied and the relationships between robots. Variation in form was a result of the timing and coordination of robots. So now we're going to show the last video.
And that's it.
Yeah, thank you.